to be discussing some of the concepts of what is a upper bound, okay, how to obtain the simple upper bound, what is that moment generating function based approach, why it is required, what is the closed form solution, the above whatever I have written over here, this is the closed form solution. If you don't get the closed form solution every time, what could be the best possible solution? That is your upper bounded solution by using some other approach, by using some Chernoff bounds. Okay, a simple bound on the average probability of error by applying the Chernoff bound. How do you obtain to your Q function? How do you obtain approximate analysis of this closed form solution? That is what I'm interested in discussing with you today. So let's start. The first and foremost thing is why to obtain a simple upper bound. Now what happens is, in order to answer this question, you need to understand, I think you have studied more or less, you might have come across the moment generating function based approach for average probability in your 6th chapter. If you have not studied, it's fine. If you have not studied, just I think usually for analytical descriptions that is used, the moment generating function based approach, MGF based approach. See, what is that MGF? Moment generating function based approach is it's a tool, that is a tool to analyze the performance of modulation in fading environments. Okay, modulation schemes, you know, that is QPSK, BPSK, so on and so forth. All modulation schemes from 2, that is generally it is BPSK, QPSK, 8 PSK. After 8 PSK, everything whatever you term here is MPSK or MQAM modulation technique. Now what is this MGF? Why we have to understand this? See, with or without diversity, or without diversity, you can apply this MGF based approach. It doesn't depend on your diversity scheme. This is a tool used to analyze the performance of any modulation scheme over a fading channel. Now you have a transmitter, you have a receiver. Now you have found out something and you have estimated the probability of error, or approximately this is equivalent to your PS or symbol error or PB bar. It depends on what kind of error rate performance that you are finding out. Now here you are finding out with or without diversity. Now one single input, single output system that is without diversity, maximum possible diversity will be 1, because only one transmit antenna and one receive antenna you have. Now this tool is used to analyze the performance of modulation scheme that you are going to use here, QPSK or QAM or whatever QAMs, whatever modulation scheme that is capital M that you are going to use, and over a fading channel, not through AWGN, because that's a non-fading environment. AWGN is your non-fading environment. Now suppose if it is relay, fading environment, how to obtain the upper bound, okay, or how to use the moment generating function based approach in order to find the probability of error. So how it can be used to simplify the performance analysis, okay, of average probability of error. Average probability of error is the concern. How do you get this? Okay. Now, a fundamental question arises in our mind if I talk about the probability of error. Now, first thing is, say something like 1 million bits of information has been transmitted. 1 million bits have been transmitted. Now, if you are receiving 1 million bits, there is a possibility that some 100 bits or some 200 bits or some 1000 bits might be lost. How do you recover that? You can't recover that if there is a complete fading environment. Because of the destructive fading environment, you cannot recover until unless if you have some kind of a coding analogy has been incorporated before it receives the signal, or before it is transferred through the detection part, the pre-detection or the post-detection part. Now, what is the probability of bit error in fading? What is the probability of symbol error in fading? That will be discussed through this. Now, what is this MGF? How well it establishes a relation between your average probability of error? That is the question. Now, simple terms, if I talk about what is that MGF and why we need, MGF is defined for a non-negative random variable gamma. Non-negative random variable. It has a distribution, right? P gamma of gamma, it has a distribution for gamma greater than 0, greater than or equal to 0. Now, whatever MGF I'm going to define, that is defined for a non-negative random variable gamma with distribution P gamma of gamma for gamma greater than equal to 0. Now, how do you define that? Usually, it is represented as M in italics like this, M gamma S, M gamma S, or M gamma. This is the notation the MGF carries. What is this? M gamma of S is equal to 0 to infinity integration 0 to infinity P gamma of gamma into e to the power of S gamma into D gamma. That's how it is defined. Now, what does it mean? This function, if you carefully observe this function, it is nothing but your Laplace transform of the distribution P gamma of gamma. So with arguments reversed in sign, that's all. So how do you can also write it as Laplace transform of P gamma of gamma, that is equal to M gamma of minus S. Okay. Now, still it is not clear what is this. The MGF for most fading distributions of interest can be computed using the closed form solution by using your classical Laplace transformation or through numerical integration. You can use Laplace transformation approach or numerical integration approach in order to find that. So generally for Rayleigh, if you talk about Rayleigh fading environment, because it comprises of both line of sight and non-line of sight environment. Now mostly it is non-line of sight path which dominates. MGF can be written as M gamma of S is equal to, that is MGF for common multipath fading distribution I'm writing, okay, 1 minus of S into gamma bar of S whole to the power of minus 1. You can write it for Rayleigh, but Rayleigh is a lot complicated. I'll skip Rayleigh because Rayleigh comes with the fact that M gamma of S depends on 1 plus k component and 1 plus k minus gamma S bar component. Okay, 1 plus k minus minus S gamma S, this component, minus S into gamma S bar component with exponential distributed component. Okay, that is little hard to find out. Let's not worry about that Rayleigh now, because Rayleigh has some severity in calculating because of some difficulty in finding out that MGF based approach. Nakagami is the combination of M. Okay, Nakagami M fading channel. This can be M gamma of S, that is equal to 1 minus S gamma S bar divided by M small m whole to the power of minus m. Now these are all some of the ways of writing the moment generating function for common multipath fading distributions. Okay. Now forget about this Rayleigh because it has one more component here, LOS plus NLOS with a dominant LOS component over here. So I'll not try to write and remember and write all those things because that has some kind of complexity over here. So we are concentrating on this and this. Now if you put M is equal to 1, it boils down to Rayleigh. Nakagami M becomes Rayleigh. Nakagami M less than 1 boils down to some other distribution. Is it possible for us to get the Rayleigh distribution from Nakagami M? It is possible with slight modifications on Nakagami M fading, so that Nakagami is a generalized fading channel where Rayleigh Height distribution, everything will fit in. Okay, now we'll not worry about all those things. That's how you can write this moment generating function. Now, why all these things are required? Now, there are two things that I want to discuss. First, in most of the situation, in most of the cases, it is very hard to, like in Rayleigh, it is very hard to obtain this closed form solution. For Rayleigh, for BPSK, it's fine. If you go for something like 64 QAM, automatically probability of error will change. So this equation will change. Now the thing is how to obtain a simple upper bound for such kind of higher order modulation schemes. Why it is required? Now, for a 2 cross 2 MIMO, it is fine. For a 4 cross 4 MIMO, it is fine. For a 16 cross 4 MIMO, it is not fine. If you are using the modulation order as 2 or 4 or even 8 PSK, it is fine. This upper bound will work. Now, if you simply increase m is equal to 16, there are a lot of issues here. You cannot go on and apply the same upper bound or same closed form solution for every value of m. Now, if you can use this, you can use this in order to get BPSK. Now, if you change from BPSK to QPSK, what happens? Something will change. From QPSK to DPSK, something will change. Definitely, the parameters will change. Now, from MPSK to MQAM, if you change, most other things will change. And in case of massive MIMO systems, where the antennas from the base station are minimum 64 to 4, 64 to 16, 64 to 64 in some of the cases. Now, for all these things, if you are going for a modulation order of more than, say, something like 16 or 32 or 64, then these kinds of closed form solutions, closed form solutions cannot be derived in all the situations. For that, you need to have bound. What is that bound? Bound is nothing but you can have an analysis by varying the values of m for different orders. You can derive some form of a near optimal solution. May not be optimal. You can call it as a suboptimal solution. Okay, at lower SNRs, and at higher SNRs, this will match with the closed form solution. The whatever equation that you have written, the analytical expressions will match with the closed form solution. How to obtain that? Is that upper bound is sufficient? Is lower bound is also required? Yes, in case of error correction coding and in most of the LDPC codes or in turbo codes, both lower bound and upper bounds are derived in such a way that in order to identify the fact if the closed form solution, suppose if it exists, suppose if that is the closed form solution, your lower bound will give you a factor and upper bound will give you another factor. So that can be derived by using some mathematical forms, by using moment generating function or by using a Chernoff bound. Usually bounds are derived by using Chernoff bound or union bound technique. Now we'll talk about, based on your MRC, whatever we have calculated so far, we'll talk about by using bounds we can arrive at a diversity order or a closed form solution in order to obtain the same results. Now, if you're talking about bounds, I will write it as probability of symbol error or probability of error. Okay, probability of error that is equal to alpha m into q function of q of square root of beta m, beta capital M, this is capital M, okay, beta m into gamma. Now this is what is written as a simple kind of substitution method or upper bounded on the average probability of error by applying some form of constants, that is alpha and beta. Now these alpha and beta are the parameters. If you have studied section 6.3.3 in your previous chapter, you might have understood the MGF approach to specific modulation and fading distributions can be, a general expression can be obtained for coherent modulation scheme in terms of probability of error PE as alpha into Q function of square root of 2 into GS or something like that you will obtain. What are that? Alpha into beta or whatever. Alpha and beta are constants that depend on the modulation. That depends on the modulation scheme that you are going to use. So if you have not understood this, don't worry. Just understand this equation. PS of gamma or P of E, probability of error, can be approximated as alpha m into Q function of square root of beta m into gamma, where this m is the modulation order. Okay. Now, by varying the values of m, different orders of modulations can be obtained, isn't it? Now, if you change it to QPSK, alpha QPSK will come, beta QPSK will come. Similarly, if you change it to, say, higher order modulation schemes, you will get higher order mod. Okay. Upper bounding using Chernoff bound is it's a generic way of explaining things. Now, in our book, what does she says is the error probability of error can be approximated by using the Chernoff bound called Q of X. Q of X can be written in terms of it is always less than equal to e to the power of minus x square by 2 to the Q function. To the Q function. That's what she says in her book, Andrea Goldsmith. For static channel gains with maximal ratio combining, you can approximate this to this equation. This to this equation. Now remember, this has to be a static fading, that is static channel with MRC. Now, what is my main intention? My main intention is to find out approximate analysis, or approximate is not a right word. This is the suboptimal way of expressing things, and that can be equated to a value where you will reach approximate value of this at higher SNRs. That's what I'm trying to prove out here. Now, if something like Q of X is less than equal to e to the power of minus x square by 2, if I write, it doesn't make any sense. Now, what does it mean? So I'll tell you one thing, just try to remember this. Now, what I want you to understand is most of these things are pretty new to you because you might have not heard about Chernoff bounds or union bounds in your previous sessions. The generic Chernoff bound can be written as, I'll write it as CB, Chernoff bound. Now, why Chernoff bound? Chernoff bound, the generic Chernoff bound of, you can call it as the Chernoff bound of a random variable x is attained by Chernoff bound for a random variable x can be attained by mi, that is Markov's inequality. So if this is the order, if it is written in the order in terms of e to the power of tx for every t greater than 0, e to the power of, if I write it in terms of e to the power of tx where x is a random variable, and for every t greater than 0, by using Markov inequality you can write it in terms of probability of, this is probability, okay, not gamma, this is probability of x of x greater than a can be written as probability of e to the power of tx greater than equal to e to the power of ta. What does it mean? The generic Chernoff bound of a random variable x is attained by Markov inequality to e to the power of tx for every value of t greater than 0 can be approximated as probability of x greater than equal to a, x is a random variable, can be written as probability of e to the power of tx greater than equal to probability e to the power of ta. Okay, that is always equal to expectation of e to the power of t into x divided by e to the power of ta. No, you don't ask me how you got this. This is another topic of study itself, so you remember this expectation of e to the power of t into x divided by e to the power of ta. Now you can generalize this term when x is the sum of n random variables like in your different fading channel conditions. Now why am I talking about x as a random variable? Because signal S, what you are transmitting, bit B, what you are transmitting is a random variable. When x is the sum of n random variables x1, x2, x3 up to xn, we get for any t greater than 0, you can write it as probability of x greater than or equal to a, that is equal to e to the, that is less than equal to e to the power of minus ta into expectation of, it becomes product of n individual terms I pi, I'll write it over here, pi I, okay, pi I into e to the power of t into x. Xi I'll write because you have n independent random variables. That's all. Now what does it mean? It means a generic Chernoff bound of a random variable x can be attained by using this Markov inequality. Now, same concept you have to apply for your wireless communication system. How do you apply? By approximation, what you have Q of x. What does it say? Q of x is less than equal to e to the power of minus x square by 2. That is what it says. Now, for this, results can be upper bounded. What did I write in the previous slide? That is probability of symbol error or probability of SE or probability of error is written as alpha m into Q of square root of beta m into gamma. I have written, okay, beta m into gamma. These results can be upper bounded. What is this gamma? This is nothing but probability of symbol error or probability of error is always less than equal to, based on this Chernoff bound, can be upper bounded. That is alpha m into Q of square root of beta m into gamma of MRC. Okay. What does it mean? It can be written as less than equal to what? Alpha m into Q of, okay, Q of beta square root of beta m into gamma MRC can be written as e to the power of minus beta m into MRC. That's all. Now, this can be written as e to the power of minus x square by 2. The same thing you have to apply here. Alpha m into e to the power of minus beta m by 2 into gamma MRC by 2. Okay, or gamma MRC. I'll write it like this. What does it mean? Simple modification, that's all. Alpha m into e to the power of minus beta m by 2. I will take this gamma MRC. I'll write it as how many branches I have? I is equal to 1 to m branches I have. I'll write it as gamma I or gamma bar, whatever. Okay, this is gamma I. Now, what does it mean? It means, come back to the original analysis, alpha m into e to the power of minus beta m by 2 into I equal to 1 to m gamma I. How do I write? How do I write I is equal to 1 to m gamma I? What is gamma I? Summation I is equal to 1 to m. I can replace this gamma I by your channel matrix. This is norm of hi square into es by n naught. Everything has been represented over here. Now, what is this es by n naught? Rho, I will call it as es by n naught. Rho is equal to es by n naught. How do you write now? If you write this is less than equal to alpha m into e to the power of minus beta m by 2 sorry, e to the power of minus beta m by 2 into, I'll take this hi bar, this is es by n naught, I'll write it as gamma bar, okay, or gamma bar or whatever nomenclature you want to follow, you follow that. Gamma bar I'll write I is equal to 1 to m norm of hi square. What does it mean? Now we are very close to the value. What is this gamma bar and what is this hi bar? Now, if you apply this moment generating function based approach, you will write the average probability of error can be found. In your book, it is simply written as PS bar integrating over the chi-square distribution for gamma of MRC yields alpha m pi I equal to 1 to m 1 by some function 1 by 1 plus something like that. How do you obtain that? In order to obtain average probability of error can be found as PE bar as less than equal to, or PS or whatever I have written in the previous slide, that is alpha m into e to the power of minus beta m by 2 into gamma bar, okay, summation I is equal to 1 to m norm of hi square. Okay, now I equal to 1 to mr, hi square is what? That is nothing but this whole term. If I replace this m by mr, number of branches, number of I equal to 1 to mr, number of branches, substitute m is equal to mr. If you get this, what is this? This is nothing but your Frobenius norm. Frobenius norm is nothing but the 1 cross whatever matrix you have. Okay, norm or all these things in the matrix fashion. If you write it like that, then it becomes less than equal to alpha m into e to the power of minus beta m by 2 into gamma bar. This whole thing can be written as h f. This term, whatever I have written over here, is the Frobenius norm. Now, why I have written it in terms of Frobenius norm is you have a MGF based approach. In this MGF based approach, you can find the expectation of the matrix. That expectation of the matrix can be written in this fashion. So usually it is written as expectation of e to the power of minus nu. I'll tell you what is this nu into Frobenius norm of h Frobenius norm square can be approximated to, can be written, it is closely written as I is equal to 1 to mr, I equal to 1 to mr, 1 by 1 plus nu into lambda IR. So if you write everything, this equation in terms of expectation of e to the power of minus means this beta m by 2 gamma bar, I have replaced it with nu into Frobenius norm. That will give you a solution I equal to 1 to mr, 1 by 1 plus nu into lambda IR. What is that? What is that R? R is nothing but your covariance matrix. R is nothing but your covariance matrix. Now lambda, you know, lambda is nothing but your principal, the eigenvalues. How do you find this R? R is nothing but R is equal to expectation of vector of H, that is channel into vector of H Hermitian. If it is complex, okay. How do you get this? This is something like H1, H2, H3, so on and so forth into here you will get H1 conjugate, H2 conjugate, so on and so forth up to HMR conjugate. If you have principal diagonal elements, the eigenvalues would be 1. That is your if you write the principal diagonal elements. What happens then? Expectation of H square into, I will write it as IMR. This is nothing but eigenvalues would add up and give you the value 1. Now, what does it mean? It means this PER, PSE or whatever is equal to or less than equal to alpha m into I is equal to 1 to mr into 1 by 1 plus beta m gamma bar by 2. Okay, gamma bar by 2. Now that is less than equal to alpha m. Okay, 1 by 1 plus beta m gamma bar by 2. Okay, now gamma I for all the branches. Okay, gamma I is equal to gamma, you can call it as average SNR. So this is what is given in the book directly. 1 by 1 plus beta m gamma bar by 2. You can replace with nu also. That's not a problem. That is less than equal to alpha m 1 by 1 plus beta m gamma bar by 2 whole to the power of this is whole to the power of here whole to the power of mr. This can also be simplified and written as this is approximate solution alpha m into 1 by 1 plus beta m gamma bar by 2 whole to the power of mr. Okay. Now probability of error for a MRC, okay, can be upper bounded by using the Chernoff bound and the MGF based approach to get this function. Now if you place MR is equal to 1, what happens? If MR becomes equal to 1, alpha m divided by 1 plus beta m gamma bar by 2 you will get. So alpha m by approximately that becomes equal to alpha m by beta m by 2 gamma bar. So what does it mean? What is the diversity order? Diversity order is your MR. Now, what is this diversity order? Diversity order is nothing but how many number of branches are active. This is your diversity order. In order to understand this diversity order, you need all this Chernoff bound approach or whatever approach you have. Okay. If you don't have, if you want to directly look at the diversity analysis from this equation, it is very hard to analyze the diversity order until unless how many branches you have, what is the modulation order you have, so on and so forth. With this approach, you can even calculate whether the system possesses diversity or not. If this becomes 1, there is no diversity. If this becomes 2, there is a diversity order of 2, so on and so forth. Okay. Now I know this previous class and this class is little hard to understand because you have never seen this Chernoff bound. So this is how it can be identified: alpha m into beta m gamma bar 1 by 1 plus beta m gamma bar by 2 whole to the power of mr. So in the limit of higher SNR and assuming that gamma I are identically distributed with gamma I bar is equal to gamma, we have alpha m into beta m gamma bar by 2 whole to the power of minus m. That also you can write. Now what is the fun in doing all these things? Now if you closely observe, whatever probability of error, symbol error or bit error, whatever you are going to calculate with this equation compared with the first equation is approximately the same, You don't have to calculate the probability of error if you cannot find it for different modulation orders, for higher modulation orders. If you cannot find it out, doesn't matter. Use this small upper bound, change the order of modulation. That's all. You will get the near closed form solution output. Suppose if the closed form solution is something like this, approximately here somewhere like this, you will get the output. Somewhere here it will start to follow after say somewhere around 10 dB. So this is one way of interpreting. But if you ask me to give a physical insight of what it is, no, I cannot give you any physical insight on what the analytical system deals about here. You have to understand the Chernoff bound and then that Markov inequality in order to derive this kind of expression. So this is one thing, and with this you have something like the two equation. This equation 1 and this equation 2 are almost the same for higher SNRs, values. If you are finding the probability of error, both equations are one and the same. Now in the exam, if I ask you to find the probability of error, you can use this equation because I will be asking only for BPSK or for QPSK. You can substitute what is that m value here, m is equal to 1 or 2, whatever, okay, and then you can change the order in order to get this. Suppose for 8 PSK, I don't ask 8 PSK and more than that, but if there is a possibility, if somebody asks you to do it, you can use this upper bounded technique and find the probability of error for MRC. Okay. Now, will this upper bound change for different combining techniques? Yes, obviously, diversity will change. Of course, this constants alpha m and beta m gamma bar by 2, that the value will be reduced compared to MRC. So this is one way of looking at the same thing. Now I'm not interested on all these things. If I substitute, I'll get the output. That doesn't make any difference to my work. What I'm interested in is if MRC gives this kind of output, MRC has also got a drawback. What is the drawback? MRC requires knowledge, channel knowledge. One of your friends has asked in the last class that CSIR has to be, yes, definitely, means that he has understood the concept. MRC requires channel knowledge, CSIR of each branch. It's not a joke. For all the branches like 1, 2, 3, 4, all the branches, if you are sending a piece of information back to the transmitter from this branch or this branch, or if you are understanding even with one transmitter, if you before combining, post combining or pre combining, if you want to know what is happening at CSI at every branch, it's not easy to implement. It's not easy to have many number of switches. For 2x4 system or for 1x4 MRRC, it's fine. Maximal ratio combining, it's fine. 1x64, it is not fine because you should have 64 RF switches, and all RF switches should be active all the time because you're using all the 64 branches. So it's not going to work out like that. Now, if it is at the base station, Still, it requires a lot of power. And look at the complexity in analyzing 64 branches. Now, what is the best possible solution? Is there any solution? Yes, you do have another solution. MRC, now we have understood that it requires CSIR, that is CSIR, channel state information availability at the receiver, it is required. Now, for each branch, it is always complex and difficult to measure, isn't it so? Are you following this? Now, at every branch, if you want to understand the CSI and if you want to measure the CSI, and based on that, you're combining, it's not a joke. Now, what is the simpler implementation for that? A simpler technological improvement. But again, if you make it simple, you have to compromise on performance. Suppose if MRC gives a performance at 10 dB, you have to use somewhere around 12 dB or 11 dB or something like that. Means you have to compromise on SNR. If you are compromising on SNR, BER versus SNR, then you can go for low complexity implementations. Otherwise, it would be difficult for us to have a simpler low complexity combining techniques. Now, what could be the low complexity alternative for this MRC? MRC is the best. You can't beat MRC, that is for sure. Okay. Now, what is the second best, if that is the case? Now, a simpler technological extension is equal gain combining. Equal gain combining. Name itself indicate equal gain combining. What is that equal gain combining? Which co-phases with each branch and then combines with equal weighting factors. What does it mean? You make all these gains as equal. You make all the gains. Gains what we have studied in MRC are based on the SNR that you have measured at the receiver, that is CSIR availability. Now I am not worried about all these things. I am just worried about making equal gain. That is alpha I is equal to e to the power of minus theta I. What does it mean? The SNR of the combiner output, assuming equal power spectral density. Equal power spectral density is nothing but n naught by 2. Okay, sorry. Okay, n naught by 2. Now, the SNR of the combiner output, assuming equal power spectral density, that is n naught by 2 in each branch, how do you represent the SNR? You can represent the SNR by gamma sigma of EGC, or simply gamma sigma you can write, that is equal to 1 by n naught m, 1 by n naught m into summation I is equal to 1 to m, okay, the received signal strength square. What is this? Assuming noise power spectral density n naught by 2 in each, I'll write it as 1 by n naught into m, okay, summation I equal to 1 to m. The distribution and CDF of this EGC does not exist because you are arranging the gains. Now, distribution function, and you have, if you want to find the closed form by using MGF approach or whatever approach, you don't get it. You don't get it because it will vary. It depends on so many factors. Now, distribution and CDF of this gamma sigma EGC will not exist in the closed form. If you don't have a closed form solution, then what are you waiting for? Then you are searching for the second best, that is the upper bound or the lower bound. We will concentrate on the upper bound, not on the lower bound. For IID relay fading with this is 2 branch. For IID relay fading with 2 branch diversity, means 2 branch diversity, I will add average branch SNR and average branch SNR gamma bar. An expression in terms of CDF can be written. That is, I have to use a Q function. If I don't have a closed form solution, then I have to use everything in terms of Q function. What did I tell you here? Here, if you are writing it in terms of something alpha m Q of square root of beta m gamma. So in terms of Q function, if I write, so this you have to remember, you try best to remember this because there is no closed form solution. P sigma gamma EGC can be written as P sigma gamma of gamma. CDF in terms of Q function, this is CDF. You know how to find out the CDF. Okay, e to the power of minus 2 gamma by gamma bar minus square root of pi gamma divided by gamma bar. This is into e to the power of minus gamma by gamma bar into 1 minus 2 times q function of square root of 2 gamma by gamma bar. I'll check once. Just wait. I'll check it in the book whether whatever values I have written is correct or not. Okay, this is 1 minus e to the power of minus 2 gamma by gamma bar minus square root of pi gamma divided by gamma bar into e to the power of minus gamma by gamma bar into 1 minus 2q into square root of 2 gamma by gamma bar. An expression for the CDF in terms of q function can be derived like this. Now you ask me a question saying that how do you derive this CDF? How do you derive this CDF? This can also be derived. Okay, this can also be derived. What are all the things you need to understand? What are all the things that you need to follow before you derive the CDF? CDF is nothing but send the pilot symbols from the transmitter to the receiver, obtain the distribution pattern, fit it to a curve so that you will get it. Now, then why do I have to believe that this CDF is correct? This is over a lot of iteration. Large number of iterations have been carried out by combining it in the equal gain fashion in order to obtain this result. Okay. Now, how do you do that? Practically, you have to do that. There is no other way. Practically, you have to do that. Then you have to obtain the CDF. Now, from this Q function, is it possible to, this P gamma can be derived? Yes, it can be derived by using one of the reference textbooks that I have given you, Gordon L. Stuber, chapter 4, okay, chapter 6, if you follow, okay, and there is one more book called Marvin K. Simon and Mohammad Slim Alauni, chapter 9, 9.8 and appendix of 9.8, okay, if you follow, you can derive, but please don't do that. You will take somewhere around 1 month to derive all those things. You please don't do that. In order to avoid that, just remember this equation. Okay, just remember this equation. What you will be asked? You will be asked compare the average probability of MRC and EGC. What is this probability of error, or what is this CDF? Now from this you can find out your what do you call the outage probability, right? From PDF, from CDF, you can find the average probability. Average probability of this is outage probability can be found out by using the same equation. Gamma by gamma bar will be replaced with gamma R. And here also gamma by gamma bar in the second function, this will be replaced by gamma bar. Okay, this will be replaced by gamma R. Okay, and similarly here gamma by gamma R, gamma bar replaced with gamma R. Your outage probability, you know. What is that gamma R? Gamma R is nothing but if you write everything with gamma R or gamma small r, okay, what is that? That is nothing but your gamma naught by gamma bar, averaged out. And you can differentiate this in order to, if you differentiate this CDF, you will get PDF. From the PDF, you can still write with respect to gamma, you will get P gamma of sigma in the closed form. Now, if you want a closed form solution, I can write the closed form solution for this also, but it's literally complicated. So for BPSK, we will talk about the probability of error. And now from CDF, differentiate, you will get PDF, obtain the PDF, and then find the probability of error for only one modulation scheme, let's say BPSK. Don't complicate things, okay? Now itself it is already in a state of chaos. Now, if you go for higher order modulation schemes, you will not study wireless communications. Okay, now for probability of error, average probability of error can be written as this is 1 by 2 into 1 minus square root of 1 minus 1 by 1 plus gamma, 1 by 1 plus gamma bar square. This is average probability of error for BPSK. Now, for interested reader, I'll write it aside. Okay, how do you do this? How do you do this? Now, what you have from CDF, you have no CDF. This, if you remember, you can solve problems. That would be fine. Just check. This is 1 by 2, 1 minus of square root of 1 minus 1 by 1 plus gamma bar whole square. Yeah, I think I'm right. Yeah. Okay, for an interested reader, look at this. Now, what you have P gamma of sigma. Okay, P gamma of sigma, that is EGC in terms of gamma. That is your CDF you have. Now, replace this with P out, means get the P out, outage probability you find out. How do you find the outage probability? Outage probability is defined in terms of P out of gamma naught, P out of gamma naught, that is 1 minus e to the power of minus 2 gamma, that is 2 gamma r, minus square root of pi into gamma r into e to the power of minus gamma r into 1 minus 2 times q of square root of 2 gamma r. Okay, this is my outage probability for EGC. Now, differentiate this with respect to gamma. Derivative, first derivative with respect to gamma will give you what? Will give you P gamma sigma in terms of EGC gamma, that is equal to 1 by gamma bar into e to the power of minus 2 gamma by gamma bar, that is plus square root of pi e to the power of minus gamma by gamma bar, okay, into 1 by square root of 4 gamma bar minus 1 by gamma bar into square root of gamma by gamma bar. And this term will remain the same, that is into the last term is 1 minus 2q of square root of 2 gamma by gamma bar. It's not so easy. This is into here, this term will come. So with this, if you integrate 0 to infinity q of square root of 2 gamma into P gamma sigma EGC of gamma into d gamma, you will get this equation. You will get what equation? This equation you will get. This equation you will get. That's how you can do it. So what is that? This can also be outage probability can also be considered. But remember this equation, because we have to analyze what is the probability of error in case of EGC, what is the probability of error in case of MRC, what is the probability of error in case of selection combining. That is all we need in our wireless communications. So what is the best possible BER versus SNR that I am going to get from all these things? What is the best possible? Okay, now always remember, if I compare this with any other combining schemes, let's say this is 10 to the power of minus 5. Okay, from here I will get somewhere around 20 dB. This is for MRC. For two branches, M is equal to 2 branches. Okay, now for first one was what? Selection combining will give you for M is equal to 2, somewhere around 24 or 25. Okay, even much 26, 27 also will get. Okay, and then next for this is for EGC. Approximately, based on the modulation scheme, 0.8 to 1.6 dB you will lose. Now, what is the advantage of this? What is the advantage of this combining technique? The advantage of this combining technique is, first one, receiver complexity is very minimal compared to MRC. How? Because you are not worried about anything. You are not worried about amplitude. You are worried only about the phases. That's all. Equal gains are available. Now, what is the another thing? Receiver computational complexity has been reduced. Hence, the design of the receiver will be cost effective compared to any other scheme. And what is the trade-off? Trade-off is you are losing, let's say approximately you are losing 2 dB, let's say 2 dB means maximum of 50% more power you may need. 50% more power you may read in order to get the MRC performance. I am not worried about this. I am just worried about low computational complexity, and I may have to push in a lot of power here, but that will be compensated with RF switches. No, most of the RF switches. Now I can group the 64 cross 4 whatever I have 64 switches into say something like 16 cross 4 switches. Equally I'll apply the gain. Equal gains are being applied. So you will get approximately 0.8 dB lesser compared to MRC. Now that is it about all the mathematics what I wanted to discuss. Now we will go to conceptual ideas and how do you implement all these things. So mathematics, yes, I completely understand. If I ask you to remember, that's not correct being an engineer, but you have a lot of other subjects to read also. So as per my knowledge for BTech, just try to understand what I have given in the class and try to remember the final equation. That is absolutely required. No matter what, if you don't understand the Markov inequality or something like that, numerical integration, numerical methods, doesn't matter, but try to remember at least the final equation so that you will know the flow of what it is. Now with that, the exhaustive part of mathematics is over. Now I'll concentrate on solving the realistic problems. Why and how? Why and how? Now I'll be giving you a simple exercise so that you can carry it out based on the equations that I have given already. Compare the average probability of error by using BPSK as the constellation point. Okay, that is m is equal to 2 BPSK that you are using. Okay, bit error rate with BPSK for under L, right? Under MRC, EGC and SC combining techniques with MR is equal to 2. MR is equal to 2. Assume two branch diversity, that is assume two branch diversity, that is your MR2 two branch. Assume IID Rayleigh fading scenario with a fixed average SNR with fixed average SNR equal to 8 dB. Okay, you can make it as 10 dB also. Approximately 8 to 10 dB is the lower SNR. 8 dB and 10 dB both you can find it out. Okay, on each branch. This will be a very important question. What I've asked you is based on this analogy what I've given. Based on this BER versus SNR, what I've given, BER or SER or average probability of error, bit error rate, okay, everything boils down to the same figure. Okay, same figure. This is in dB. Okay. Now, what I've asked you, assume Rayleigh fading scenario. Find out what is going to happen with the average probability of MRC, EGC and selection combining with branches 2, and you have to assume IID. Now what you have to do? You have to substitute this equation in order to get MRC. Substitute what is M? M is equal to 2. Substitute, get it. Now you will get some value. Some probability of error you will get. Let's assume for MRC, some probability of error you will get. Okay, let's say it will be in the order of 10 to the power of minus 3. It will be in the order of 10 to the power of minus c. Now, if you calculate it for based on this equation, okay, 1 by 2, 1 minus square root of 1 minus 1 by 1 plus gamma whole square. If you calculate gamma, you know, if you calculate for the fixed SNR, that is probability of error for EGC, this will also you will get in terms of 10 to the power of minus 3. But here the value will be less, here the value will be more. And this difference, what I've talked, is in terms of 0.8 dB to 1.6 dB or 1.7 dB. It depends on what kind of modulation order you have used. That is the difference. Means you are approximately getting the same performance with equal gain combining. Now, if you calculate the same for selection combining, you will get it in the order of 10 to the power of minus 2. Means you are already getting an error flow at 10 to the power of minus 2. At 10 to the power of minus 2 itself, bits will be lost. Somewhere, instead of a waterfall curve, you will get somewhere like this. Even if you push in a lot of bits, you will approximately need higher SNR, say at 15 dB instead of 10 dB, you will get this one, 10 to the power of minus 3. Means what? You will lose somewhere around 3 to 4 dB of SNR if you use selection combining, 0.8 to 1 dB or 1.5 dB SNR if you use equal gain combining, and this is the best possible combining that you could ever wish to have in receiver combining methods. Now, there is one more practical advantage, one more practical idea I can give it to you over this kind of technique, where what could be the maximum time limit that you can fix in order to obtain this output? What could be the best possible time limit so that you will have so and so outputs in a calculated way? Now, this you can solve, isn't it? If you have any difficulty, let me know. I think this you can solve. And there is one more important aspect, one more important communication system problem. A radio communication system has to be designed, okay, has to be designed to work on radio channel, radio channel exposed to okay, flat relay fading, okay, relay fading. A time availability of 99% is required okay, for the system to operate properly, okay, to operate properly. The receiver is assumed okay, to work satisfactory with a signal power of approximately 5 dB above the noise power, Now, this you have to understand. Above the noise power, what are all the things to be calculated? First, calculate the required mean SNR to obtain the required time availability. To obtain the required time availability. Time availability. What does it mean? I'll explain what it is. Okay. Next, what is the required mean SNR? Mean SNR. If a two-branch diversity scheme, mean SNR with M is equal to 2 or MR is equal to 2 or N is equal to 2, NR is equal to 2 or branch is equal to 2, if a two-branch diversity scheme with selection combining is introduced. So such kind of design-oriented problems will be asked. What does it mean? What he has asked, a radio communication system has to be designed to work on a radio channel exposed to flat relay fading. A time availability of 99% is required for the system to operate properly. Okay. The receiver is assumed to work satisfactorily with a signal power of approximately 5 dB above the noise power. We don't know what is the noise power. It is approximately above the noise power. Now with that, calculate the required mean SNR to obtain the required time availability. What is the required mean SNR if a branch M is equal to 2 with selection combining has been introduced? Now, whatever he gives, don't worry about the crux of unnecessary ideas that he has given. What you have to find out, you have to concentrate it. Mean SNR to be obtained with required time availability. What does it mean? For a relay fading channel, the distribution function you have to understand. What is the distribution function? 1 minus e to the power minus gamma by gamma bar. The time availability is given by the probability that signal exceeds the level of 5 dB. 5 dB, how do you convert 5 dB? If you convert it into anti-log 10 to the power of 5 by 10, whatever, you will get in the linear scale. Okay, from dB to linear scale, you have to convert. The time availability of 99% you have. So the time availability 99% corresponds to P gamma of gamma, that will be equal to 0.01. So first what you have to calculate is gamma by gamma naught. Gamma by gamma naught you have to calculate. That is natural log of 1 minus P gamma of gamma. That's all. So gamma naught you find out first. You will get a value in terms of a linear value you will get. First, if you calculate, you will get value in terms of linear scale. So gamma bar or gamma naught, whatever it is, you calculate that. So if you can calculate that value, gamma by gamma bar, you will get a linear scale value, convert it into SNR. Then time availability problem has been solved. Now what is the other, for a two-branch diversity scheme with selection combining, the distribution function is what? CDF is 1 minus e to the power minus gamma by gamma bar whole square. So e to the power of gamma by gamma bar whole square is 0.9. That is because of e to the power of minus gamma by gamma bar whole square. Gamma by gamma bar value you know. So e to the power of minus gamma by gamma bar whole to the power of 2 will be approximately 9.9. So find out gamma bar. You will have another value here. Convert it back to SNR. Now you need to understand two things here. First thing is how to find the time availability. 99%. What does it correspond to? 99% correspond to P gamma of gamma, that is equal to 0.01. What is the availability? The time availability of 99% corresponds to the proper operation. The time availability of 99% is required for the system to operate properly. So first find the mean SNR, the required time availability. Mean SNR M is equal to 2. With selection combining, if you introduce, you will have a difference. Now, after this, if you plot, you will come to know without diversity, what is the SNR? With the diversity, what could be the SNR that is required in order to get this? So for a given SNR of whatever 5 dB over the noise power, this selection combining, even with small selection combining, drastically reduces the SNR to an order of magnitude, say somewhere around 10 dB reduction will be possible. Similarly, it can be extended to your MRC in order to obtain what is that SNR. So these kind of stuffs can be thought of, and one of the ideas that you can think of in order to improve the performance, and you can also include switch and stay combining, switch and examining combining, or whatever, in order to analyze the performance. So that is for all techs and researchers who are interested in that area. But this kind of problems you can think of. You try these two problems. If you have any clarifications, that if you find any difficulty, I'll solve it in the next class. So this is it about the combining methodologies and diversity and whatever it is at the receiver side. Now we have to talk about what happens if you have the same scenario at the transmitting side. How do you obtain the transmitting diversity thing? We'll take 2 minutes break, and if you have any clarifications or question, you please go ahead and ask.
अबे बहुत डिंक है हेडशॉट पाया 1 of
Go to one OP. Hold कर बस उसको जाने दे
Okay.
Go to one OP.
Fine, I can sense a lot of difficulty in understanding the math part. That's okay, fine. Brush up your linear algebra M3 basics. One of your classmates has exhaustively worked on so many aspects, and one of your students had asked a generic doubt on how to implement all those things. So wonderful doubts. I felt very happy for the hard work that you have put in, and keep the good work continuing all the time, so that you will understand more and more mathematical part of it. Though wireless communication physical layer perspective, this is little old compared to the 5G what we are studying today. But without this, you cannot design any other channels. So that's what I feel. So these basic essential tools are required in order to understand all these things. Okay. So some fundamental doubts and any conceptual doubts, if you have, please go ahead and ask. Anything? Okay then. Now we'll go to transmit diversity analysis. Transmit diversity analysis. Concentrate. Please try to concentrate, because this is complete idea, not a mathematical part. Now, till now we have designed, understood at the receiver part. Now we have to understand everything. Now till now, this is what I have, something like this, something like this, something like this, and I have a combiner, so on and so forth I had. Now, this is what I have. Combining, so on and so forth I have. Now, what do I have in the transmit diversity analysis? In the transmit diversity analysis, I have the same thing from the transmitter. That is, I have multiple transmitting antennas. I have not gone into MIMO yet, but this is how the combination works. I have a single receiver. The performance of all these things would remain the same if you are getting transmit diversity and if you are getting receiver diversity. If you are calculating the probability of error for the transmit diversity scheme and for the receiver diversity scheme with 4x1 or 1x4, whatever you do, diversity order, rank of the matrix, and your performance, probability of error, and the average probability, whatever you do, all will remain the same. It won't differ. For a 4x1 system and for a 1x4 system, you will get the same diversity order, same performance analysis. It will never change. But what if, now you tell me please how the transmit diversity comes into picture here. Transmit diversity, how well you can obtain the transmit diversity. I have to send this information 111001. This 10 bits of information I need to transmit from. I need to transmit from 4 transmit antennas and 1 receive antenna. That is generally represented as NR cross NT. That is usually represented as 1x4. You can write it as NT cross NR also, but you have to mention what is NT, what is NR. That's all. Now you please tell me, how do you obtain the transmit diversity? Now I need to send, let's say, I need to send this 4 bits of information. How do you send? Anyone? It's not so complex. Anyone? Go ahead, please answer.
So we need to divide the transmit power equally between each antenna and then send the same information, that is the same bit.
You wait. Just wait. You had exhaustively worked on it, okay? I really felt very happy for you because you have understood the core essential mathematics part of it. Very good, very nice. Now, please, others, you just think of it.
आराम से
Others,
खेलते रहिए.
Adarsh, Ashok, are you there? Anyone? Suraj, Aryaman? How many of you are sleeping? Just raise your hands. I know I'll get some 200 hands raised. So look at this. Look at this concept. Now, there are very high possibilities here. Now, if you have 1 cross 1 system, let's say you have only 1 cross 1 system, what you have to do? If you are using BPSK or QPSK, you have to perform something like this. Let's say if you have QPSK, that's a dbit, 2 bits and 2 bits of information that has to be transmitted. Something like 4 bits of information, if you want to transmit, you should have some QPSK kind of constellation. Through this, you need to transmit. Now, if you have 2 antennas, now if you have 2 antennas, is it possible for you to transmit something like this? 1 0 from first antenna, 0 1 from second antenna. Is it possible for you to transmit this? Transmit like this? Anyone?
Walker message bhai.
Is it possible for me to transmit something like this over all the 4 antennas? Let's forget about this. Now I have 8 symbols, 8 bits of information. 2 2 I have 1 0 from one antenna, 0 1 from another antenna, 1 1 from one antenna, and 1 0 from another antenna. Is it possible for me to transmit all these things, something like this, and to obtain a transmit diversity? Anyone? Anyone?
तू वर्ल्ड करके ना बी चले जाना, ठीक है?
Please go ahead. Give a wrong answer. It doesn't matter.
तू अंदर आना.
No sir, do all of them have
सब
to
लोग
be
चलो
same?
ए पे, वर्ल्ड कर देगा बी पे, फिर आप लोग रिटर्न चले जाएंगे.
Why? Why do you think so?
इसके आगे नहीं जाने का और इसके आगे नहीं जाने का.
Why do you think like that? What
थोड़ा
happens
सा होल्ड करके लेकिन चलो उन्हें
if I transmit
रोटेट होने दो
a
एक की तरफ.
different bit of information? What happens? It is possible, but there are lacunas that you have to address. It is possible. Now, what are you transmitting out here? Just what are you transmitting out here? You're transmitting 8 bits of information from 4 different antennas. What are you losing? Now, if this H has a different path, this H has a different path, this H has a different path, this has a different path. Now, if you lose because of LOS or NLOS, because of fading environment, because all H's are different. No? H4 is different, H3 is different, H2 is different, H1 is different, because we have assumed uncorrelatedness between the transmitting antennas. Now, if H4 goes for a deep fade, you will lose this 1 0. What you will get? You will get 1 0 0 1 and 1 1 only. But you have lost these 2 bits of information. So this kind of analogy has been ruled out. Now what do you have to do? You have to do 1 0 1 0 1 0 1 0. Is this the way that you are going to transmit in order to get transmit diversity?
Okay.
Yeah. The thing is, in transmit diversity, you have multiple transmit antennas. And as one of your friends said, yes, Yuvraj, I believe, Yuvraj said, the transmit antennas, the power has to be divided equally among these antennas so that transmit diversity can be attained. Now, where are you going to get all these kind of stuff? Where you have base station which doesn't depend on the battery power, because it usually needs a lot of high power, because the distance of communication from base station, the base stations and the sectored beam antennas will be very high. So it will be somewhere around antenna 64 antennas or 128 antennas can be installed with MIMO or massive MIMO systems. It requires a lot of megawatts of power. It's not a joke. There is something like Earth power model. Earth power model. I don't remember the number, 251 or 231. I don't remember that. There is an Earth power model which will describe what exactly the power which is required for a 4x2 system, for a 4x4 system, for an 8x4 system, for a 16x4 system, so on and so forth. Okay. Transmit diversity design, which is always dependent on this H. What does it mean now? It means channel state information availability at the transmitter you need. Isn't it so? Now here, channel state information at the receiver, okay, that is fine because there is complexity, but equal gain combining I'll employ. Still, I can reduce the computational complexity, but CSIR is easy, but CSIT is difficult because why CSIT is difficult? Because you have many number of antennas, not 4. It is not restricted. It is 16x4. It is 32x4. It is somewhere around 128x4, something like that. So the transmit diversity design depends on whether or not the channel complex gain is known to the transmitter or not. Means whether when the channel gain is known, the system is similar to your receiver diversity system. CSIT, if you know the CSIT, it is nothing but your receiver diversity system, but the performance of receiver diversity and transmit diversity system will be uniform. When you don't know what happens, when you are not aware of the CSIT, what happens? Any guess? Any wild guess? Now I don't have channel state information availability at the transmitter. At the transmitter, I don't have. I have channel state information availability at the receiver. That is not complex. I can go with 1x MRRC system. That is fine, accepted. But how do you obtain the transmit diversity in that case? You can obtain the transmit diversity in that case by utilizing one more dimension called space and time. That is, space and time diversity can be employed in order to obtain this transmit diversity gain. That can be discussed later when the channel state information availability is not available. When channel state information at the transmitter is not available. Now, try to understand the fact. What happens?
Blind use karo na apna rehna ki ghar leke jayegi kya blind
is not available means this is not available. CSIR is available. This is available. Now CSIR pertaining to the channel state information availability at the receiver. This is very less complex compared to channel state information availability at the transmitter. Now look at this.
Camping karo, logo maar do.
Take a mobile communication scenario. What happens to the mobile communication scenario? You have a base station over here. Base station sends a piece of information to the mobile station will receive. Now, you have handoff strategies. Something like now this is not used nowadays. Now, MAHO is mobile assisted handoff. Mobile assisted handoff. What does it mean? I know my channel state information availability at the receiver. Mobile control means I know my channel state information availability at the receiver. I don't know what is happening at this. I'll be sensing the signal strength. That's all. Signal strength will be forwarded to my transmitting antenna or to my nearest base station so that I will ask the network, this network to call for a handover. Now this is not used. Okay? That is one kind of technique. First one is mobile assisted handoff. Second one is mobile controlled handoff. The third one is network controlled handoff. Network controlled handoff is generally not used. Only mobile controlled and mobile assisted handoffs are assigned. Now you know that cell structures, cell geometry, why it is like this and so on and so forth. I'll give you a proper example of why exactly CSIR availability has to be required. Now mobile is traveling somewhere from left to right. Now the SNR availability or the signal strength from this base station is available till this point only. Now there is another base station over here. Another base station, the signal strength of this base station is available to this cell and to this cell also. Now my mobile moves along this direction from X to Y, in this direction. What happens at this stage? I need to get a handoff from this cell, the red cell, what I'm currently working on now to the next nearest cell. Let's say this is A, this is B, and this is C. Now I have to get a handoff for this cell or to this cell or to this cell. Now, whichever the strongest signal I have, my mobile will be detecting completely what is happening around me. That is my channel state information availability. Channel state information availability. This is a rough example I'm giving you. This is not exactly what channel state information availability, but to understand, to make you feel about what is the network signal strength. I have one signal or two or three dots or four dots, whatever the percentage of, say 33%. I have, let's say 33%, only 2 sticks I have. Now what does it mean? I am having a lower signal strength. Now the threshold is 16%. Now if this threshold signal strength, if it reaches to 16%, this automatically my mobile station will request the base station to transfer my channel to a next nearest station. So the mobile, when it moves, the next available channel will be allocated to my mobile device. And user will not come to know what is happening. Now what happens if it is less than 16%? This is my threshold. If it is, say, somewhere around 9%, let's say. Now if you are on a call, the call is said to be dropped. That is called a hard handoff. Now if the call has been transferred smoothly, and if you don't know, if you are in the next cell, that is a soft handoff. You know all these things, but still. Now what is the channel state information availability with this? The signal strength, received signal strength indicators at the receiver will be transferred back to the transmitter, based on the signal strength what you have attained at the receiver. Now don't get confused with the channel state information availability at the transmitter and the channel state information availability at the receiver. Now channel state information availability at the transmitter is very complex because lot of antennas are required, and channel state information availability at the transmitter is always complex compared to channel state information availability at the receiver, because receiver is a handheld device, maybe portable device. That is why now you can argue in another way. Suppose what if your mobile has the capability to install 64 antennas, then CSIR becomes difficult. Even in that case, your 870 Snapdragon whatever chip, even if you have 16 transmit and 16 receive antennas, still these are patch antennas, are small aperture antennas. Both CSIT and CSIR with synchronization can be installed and can be operated with a active hybrid beamforming. You can still go with that conclusion, whatever 16 cross 16 you have. But that is not our case. Our case is, what if channel state information is available at the transmitter? How will you get it? Now you can get it through the reverse paging channel or a low frequency feedback channel from the receiver, so that you will understand what is happening at the channel state information, what is happening at the transmitter. Or you will have a relayed system for you can call it as a relaying system. Relaying system will take care of what is happening till this point at the transmitter, and it will send it back to the transmitter saying that this is the signal strength here. Even most of the receiver does that. Okay, most of the receivers will. But the channel state information at the receiver of a mobile device, what is that 30% I have, will be controlled and will be communicated to the transmitter only based on the requirement, not all the times. Okay, not all the times. But it will be searching throughout. So this is one concept where you need to understand what is CSI, what is CSIT, what is CSIR. Now CSIR is lesser complex compared to CSIT. Now what if CSIR is available, CSIT is not available? CSIR is available, CSIT is not available, and you don't have any other paging channel to transmit the received information to the transmitter. Means I don't know what is happening at the transmitter. Only channel state information availability at the receiver I know. Now you tell me what happens to the state of the system. Now, in case of that, transmitter simply cannot transmit whatever it requires. Okay, you cannot simply go on transmitting whatever you need, like BPSK, QPSK. Now you don't know what is happening at the. You don't know what is happening here. You only know what is happening here. Now, if something goes for a deep fade here itself, you know what is happening at CSIR, but you don't know whether it is received or not,
Well,
whether it is received or not properly.
Guys, come on.
Now, usually CSIT and CSIR can be estimated through proper channel estimation techniques, so that based on that, gains will be allotted based on the channel. Okay, gains will be compensated with weights will be approximately used at the transmitter itself if you are using transmit diversity approach, so that you will get a better performance analysis. Okay. Now CSIT you know, CSIR you know. Now CSIR I have, CSIT I don't have. What happens to the state of the system? Do you lose something? Do you lose something? You don't generally you don't lose anything unless if you manage it properly. But the trade-off is you lose little bit of performance, like 50% or 30% or 40% based on what kind of 90 analogy you are implementing. You lose performance. Now what is that? How will you lose that? Now how do you lose that? With a practical example, I have to explain how do you lose that. What are all the disadvantages pertaining to this diversity scheme so that you will lose that performance? Anyone, can you explain why you will lose that? Why you will lose this kind of what do you call the practical limitations of diversity?
पिंग 400 पे चला गया, मुझे दिखाई नहीं दे रहा भाई कुछ.
Now the practical limitations of diversity scheme is practical limitations. Practical limitations. There are three limitations. First one, pre-detection and post-detection combining. Pre-detection and post-detection combining. Post-detection combining. First one. Second one. What is the second one? You know anything? Correlated branching. Correlated branching. Blind the side pe, Rina. Third one, because of the correlated branching, there is the effect of correlated noise.
भाई क्या aim है
correlated, sorry.
ना
ऐसे करके थोड़ी होगा भाई. रेन अब घूमे जा रही है, ब्लाइंड भी नहीं दे रही.
Correlated
नहीं था उसका, इसमें ब्लाइंड आई नहीं.
Noise. Okay, effect of correlated noise. These three we will try to understand properly. Then we'll go back to the same example and how to improve that we will try to understand.
नहीं आएगा वो भाई.
So first thing, pre-detection and post-detection combining. This is with respect to the receiver. This is with respect to the receiver. Combining, whatever you say, pre-detection and post-detection combining. So the diversity receivers performing post-detection combining.
Time नहीं है भाई, क्या कर रहा है?
What is that? Post-detection combining means what? The signals detected before combining. Post-detection combining. Post-detection combining means signals are detected before combining. That's all. Now what happens in this? In the pre-detection combining, what happens? The signals are first combined and then transmitted. Means the first combined and then detected. So there are two different implications to these things. Pre-detection systems are usually these pre-detection usually more complex. Why? Because in pre-detection systems, what happens? First signals are first combined and then detected. Now the detection rate or the probability of error in detection is more because you are simply combining everything and then you are detecting the symbol that is transmitted or the waveform that has been radiated. So these are usually complex and costly. So combining before the detection gives combining before the detection. What happens in combining before the detection? What happens? Combining before the detection, less switching transients, isn't it? Less switching transients. So it will be less complex compared to your pre-detection combining. Now what happens is combining before detection, less switching transient. How? In selection diversity you use selection diversity, selection combining or selection diversity if you use less switching transients, switch and stay combining, that's all. So you have to understand one thing, where exactly the combining is performed. Usually combining is performed at the IF level. So the individual down converters, amplifier, co-phasing circuitries are always required. So co-phasing is always required to satisfy the requirement of the complete system. Now this is transmission, this is reception. If you have a proper synchronization between the transmitter and the receiver, if you have proper co-phasing circuit, then only this coherent summation of equal gain and maximal ratio combining will work out. Otherwise, if you don't have a proper synchronization, that is nothing but your phase lock loop that you have studied in frequency. If you don't have phase which is locked properly to your incoming signal, then what happens? There will be successive delays. You might have studied about that. What is that? Lock range and capture range. Okay.
Oman, so backstep karo,
the reference signal for phase comparison can be either one of the incoming signal or the combining signal itself. Then you lock it. Now this is for coherent combining. This is fine. For non-coherent combining, it's not the case. So in the post detection receiver, generally it is much simpler to implement. RF co-phasing is not required in case of your post detection combining. So co-phasing is not necessary because detection is performed before combining itself. So you will come to know what is the symbol that has been radiated already. You will detect the symbol. So probability of error is it's very good. Probability of error is means it is competitive compared to the pre-detection schemes. And switched combining, sometimes with selection combining and post detection combining can be used in order to get a better performance here. So that is about pre-detection and post-detection.
Good comeback, guys.
Correlated branching, correlated branching deals with what kind of transmitter diversity or receiver diversity you are planning to implement. Now, if you have, let's say you have only one active transmitter and 3 active receivers. Now, even in case of these receivers are separated by a distance of lambda by 2. If these detectors are not separated by lambda by 2 distance, then you have correlatedness. Even if the channel undergoes uncorrelatedness, if the channel is uncorrelated, but the branching of the antennas has not been met properly, still you will have receiver correlation comes into picture, and you will have correlated performance instead of getting uncorrelated performance. Same happens with your transmit antenna diversity, means transmit antenna diversity performance also. If you don't have lambda by 2 separation between the transmit antennas, before it enters the channel itself, it is already correlated. It is already correlated. Now what happens if the channel gives some correlation and you have correlated already? Channel mimics the performance of transmitter 1 and transmitter 2, and it is impossible to separate it out because you are standing from the receiver standpoint and you don't understand what is what. Transmitter 1 is also transmitting the same information, and transmitter 2 is transmitting the same information, maybe with a different phase. And if the wavefronts are 180 degree apart, then you have destructive interference. So that is about your correlated branching. It is important to study the effect of signal correlation before you transmit. One could expect moderate correlation always. So that is, I have given you the value probably lambda by 2. 0, 0.5, usually it is represented as rho, and 0.9. 0.9 is the dense correlation, moderate correlation, no correlation. This is moderate, this is no correlation, this is dense correlation. Okay, this is the correlated branching. Now I'll tell you a simple
blind take bhai upar ek bas blind take de
approximation. I have one antenna here, second antenna here, third antenna here, fourth antenna here. Now if my base station is designed in such a way that I have to transmit all these things with a lesser lambda by 2 distance, then what happens? Now if it is an array, then I can have a lambda by 2 separation between transmitter antenna 1 and transmitter antenna 2. Now if I don't have an array, if it is circularly placed, something like this, antenna 1 here, 2 here, 3 here, 4 here, then how do you place it? This is very important. Anyone?
Fuck.
Are you getting my question? If it is circularly placed, if all the antennas are circularly placed, antenna 1 and 4 may not have uncorrelatedness. It still possesses correlatedness. How do you perform? Any idea? Anyone? If the antennas are placed in this fashion, then you have to maintain a minimum distance of lambda by 2 between the antennas which are opposite to each other. So you start to radiate this as first antenna, this as second antenna. And third antenna, and this third and fourth antenna have to be separated by a λ/2 distance. Now you have to avoid transmitting from 1 and 3 antennas because they are correlated. You have to avoid transmitting from 2 and 4 because they are correlated. But if you do that, you will lose spectral efficiency, isn't it? You lose number of bits because all the antennas you are not making active all the time. So in order to do that, if you still want to continue with that, these two will exhibit correlation, these two will exhibit correlation, but minimum correlation with different phases have to be incorporated for the correlated antennas or antennas which are placed nearby. Are you all with me? That's how you can avoid that correlated branching approach. And correlated noise is also similar kind of thing where that is the most difficult situation that is obtained when the noise has a positive covariance matrix. You know what is covariance matrix, no? If you have noise which has a positive covariance matrix, what happens? No, expectation of ni conjugate will be equal to rho. Now the variance E into ni square will be equal to 1. Now what happens? Uncorrelated noise, expectation of n square is equal to m. That is what we have studied. It cannot be m if you have positive covariance. When your positive covariance matrix will occur, which can occur only when combining after the detection is used. The noise is mainly due to external noise, not because of any other thing. Now, AWGN will get added into the system, so you might experience that positive covariance matrix. You have that difficult situation due to external noise like thermal noise or whatever it is, then it is impossible for you to have the diversity order. Otherwise, you will have a diversity order of maximum branches. Even if you increase number of antennas from 1 cross 1 to 4 cross 4, if you have all these problems, diversity order will go to 1 only. Tell me how? A very important aspect. Try to concentrate on this. This is not a mathematical concept. So I'll give you a realistic example of what happens in case of a correlated thing. It's out of linear algebra and out of the interest that linear algebra created. You can still write how exactly you can simulate and prove the trade-off or how it becomes one. Now you've studied rank of a matrix, right? Rank of a matrix. What is rank of a matrix? Rank of a matrix, anyone? Rank of a matrix? Rank of a matrix, you know, anyone? Number of linearly independent what? Anyone, please? Number of non-zero rows? Yeah, correct. Number of non-zero rows. Okay, what does it mean? It means if you have something like rank 4 means at least you might have used 4 transmit and 4 receive antennas, isn't it so? If your matrix says in the wireless communication perspective, if you are using NT cross NR as 4 cross 4, if you say the rank of my matrix is 4 means H, whatever I have obtained, will be a full rank matrix, isn't it so? Hello, are you there, all of you? Now here, if my H gives a full rank matrix means performance will be very high. Performance, probability of error is, it's very good. It's very good. Suppose if my rank is, let's say 1, for a 4 cross 4 system, if my rank is equal to 1 means either these 4 rows, number of linearly independent, means one row can be represented with other 3 rows, isn't it so? When this scenario happens, I think all of you have experienced this, all of you. Not in case of correlation, Correlation, yes, it happens. Not this drastic kind of stuff will happen. Correlation, yes, it removes, yes. Correlation can happen. You please tell me when, not in case of correlation, even if it is uncorrelated, when does this happen? When does this happen in practical scenario? Anyone? Just think about it. Now, if you are traveling by train, if it enters the tunnel, what happens? You lose all the signal strength, isn't it? Why you lose the signal strength? Because signal has not been propagated properly. The drawback of the entire ray from transmitter passes through a tiny opening to reach the receiver. That will be blocked properly, isn't it, sir? The cause and effect of this situation is scattering exists, both the transmitter and the receiver edges. So this scenario, whatever I am explaining, reduces the rank of the matrix. Reduces the rank of. Now you are passing through a tunnel. Let's say you are passing through a tunnel. Tunnel may not be straight all the time. It may have curvatures also. Now it may have something like this. Now, even if you have 4x4 here, 4x4, even if you transmit 4 signals here, what happens here? You may not be able to receive all the 4x4 signal strength. This kind of situation generally do exist in our practical scenario, practical systems. Then what happens? This becomes a simple channel with receiver diversity. This becomes a MISO system. Or if it passes through properly, even if you have something like 3x3, what happens? The scenario is similar to MISO system, cascaded with SIMO system, single input multi-output system, cascaded, then it becomes multi-input single output system. What happens? These 3 rays has to pass, but what happens? Because of the block, only 1 ray will pass with a higher signal strength. This kind of effect is called as a keyhole effect. Keyhole effect. Keyhole effect. Look at this. The effect of keyhole is observed in many practical scenarios. If you go underground, if you go through a tunnel, this kind of you may have 3 antennas which are transmitting piece of information, but because of a small aperture at the beginning of the tunnel, you may not experience, or the signal strength of the signal, or signal strength will not be transferred properly. So what happens? It minimizes the degree of freedom. It minimizes the degree of freedom. You are supposed to get a degree of 3. NTR, NRS 3, degree 3 or 4, whatever. Okay. Now it has reduced to D equal to 1. Even if there are many scatterers and widely spaced antennas at the transmitter and receiver, because of this spectral efficiency of a pinhole channel gets diminished because of the rank deficient matrix. Rank deficient matrix. Very important concept in your millimeter wave communication and in 4G, beyond 4G or 5G communication systems. What happens to the state of a keyhole channel? It will be relay only. It will be relay only. The thing is, there exists a keyhole effect. That might turn into Raishan also. In case of indoor environment also, you may experience indoor wireless, corridor or underpass, subway, tunnel, anything. So in order to do this, you may have to install repeaters inside the tunnel in order to enhance. Nobody will do that, okay? Because that becomes more complicated. So instead of that, cooperative communications employing amplify and forward relaying can be. That is nothing but your relay node only, right? So amplify, forward, and something like that can be used. Now there could be a question where show that mathematically or analytically a rank of a keyhole channel, KCH or KCX, keyhole channel. This is generally, it is represented as a rank of a keyhole channel or rank of a keyhole channel for a 3x3 system. For a 3x3 system is always equal to 1. How do you show that? It can be shown. You have to transmit some symbol, okay, multiply it with left symmetric matrix H1, H2, H3, X1, X2, X3. You will get a term. The secondary keyhole is given by some alpha. Now you have to understand this position. What happens? Only one signal will get through. Now if you multiply, you can represent these two waves as a single wave. Now what happens if you write H becomes equal to, say, something like I'll write it in terms of, let's say, H1, H2, H3, something like I'll write it as H4, H5, H6 here. Similarly here, H5, H5. Okay, I'll write it properly. H, if you have a 3 cross 3 matrix, okay. Now you will have H1, H2, H3. Okay, here H1, H2, H3. Here also H1, H2, H3. This is my channel. Okay, now you will get somewhere around, let's say I will have a complex number. I will call this as H4. Okay, I will call this as H4. You will get H5 here. H5, H5, H5 here. This H6 you may get here. These H5s and H6 can be represented. The second row and the third row can be expressed as a first row. So the rank of the channel becomes 1. So there will be no gain, the multiplexing gain or some gain you won't get. And the diversity order will drop down to 1 only, even if you are using 3 cross 3 or 4 cross 4. Okay, this with mathematical approach we can solve actually. I'll do that. Okay, but you got the idea, right? You got this idea, right? Now, one more practical example I will give you. Practical example. Now you are on a train. This, let's assume this is a train. Okay, let's assume that. Okay, you have a mobile device. Now it is traveling at a speed, a Doppler speed of say somewhere around 160 kilometers per hour to somewhere around 320 kilometers per hour. Now you have cell terminology here, cell structure, everything is here. Now within no time, within fraction of seconds, it will cross cell boundaries. Isn't it so? This train will cross cell boundaries within second. Before it gets a handoff, it might have moved to another cell. If you are on a call, definitely you don't get that call connectivity. The same happens in case of tunnel also. If you are on a call, automatically the call set to be dropped, hard handoff, because there is no signal strength. That doesn't mean that you don't get signals inside the tunnel. You will get the signals. Even if you amplify and forward it, only a small amount of reflected wave or scatter wave will be there. Okay. Now, if a train moves at 160 kilometers per hour and or 300 kilometers per hour, it will within no time it will go out of the cell 1 to cell 2. How the handoff takes place? How the handoff takes place? How this handoff takes place? Is there any transmit diversity or receiver diversity scheme that we can derive in order to have a proper call connectivity or call establishment can be made between cell 1 to cell 2? And suppose if you're using data, that is fine, that's not a problem. If you are on a call, automatically call is set to be dropped somewhere here before it is getting connected to another cell. How do you manage to get a handoff here? This is another practical case scenario, okay, study. So there are a lot of amplifiers that has to be placed before at the engine and at the last bogie of the engine of the train, so that these amplifier and forward relays will work as a repeater, so that the call is established with that cell for some amount of time. Even if the train moves at 500 kilometers, then no repeater will work. Okay, up to a maximum of 270 kilometers, the call can be established. This is what I have studied from 2016 data that has been gathered from France fastest train. Okay, but if it goes beyond this, then you need to increase the frequency, and that will happen beyond 4G or in 5G, not in case of any other technologies. The call is said to be simply dropped. Okay. Now, what it has to do with our diversity analysis? Whether you have 3 cross 3 antenna, 4 cross 4 antenna, 100 cross 100 antenna, doesn't mean that it will give you a diversity gain. It will not give you a diversity gain, though it is coherent, demodulated, and detected. Okay. Now, those are all the 2 case studies. Try to solve the problems, whatever I had given, not these problems. Okay. The problems whatever I had given earlier, okay, those 2 MRC and EGC problems and the time availability. And that keyhole channel, I'll show it to you, show that the rank of a keyhole channel for a 3 cross 3 MIMO will be equal to 1 by mathematical conjecture or proof. That is not so difficult, but it can be with some ideas you can implement. For that, you need to understand the different perspective of multi-input, single output, single input, multi-output configurations. Now, this is it about CSIT availability and unavailability. What is the strategy that you are going to implement if you don't have a CSIT? And if you only have a CSIR, I am ready to compromise on some performance issues, but I have to reduce the complexity of the circuit. If that is the case, how do you go with it? In 1998, one of the famous scientists by name, Professor Shiva Zalamoti from Iran, he has developed a method called the transmit diversity approach in wireless communications. He had worked for about 2 years for that. Okay, simple transmit diversity in wireless communication scheme, that is the paper. And he has implemented beautifully how rugged the system will behave, and what are all the consequences of not having a CSIT availability, and how do you develop a system which is low complex and still gives you a approximate analysis, or you can still get a performance which is equivalent to your CSIT performance. Maybe 1 or 2 dB less, but still you can hope without CSIT, without sync, without the data which is synced at the transmitter port. How do you obtain that? That we have to study. Please don't miss the next class. If you miss the next class, then it will be very difficult for you to now itself I'm witnessing that most of you are not even interested in asking doubts today because of a lot of mathematics. So if you miss the next class, Alamoti scheme you don't understand anytime. You can read and understand, but the physical insight of Alamoti, it's very hard to understand if you are a beginner. Okay, unless if you have a strong math behind it, you will not understand. So don't miss the next class. We will talk about how beautifully he has implemented that scheme, so that just an extension, just a simple extension, even if you don't have CSIT, how beautifully you can improve the performance. May not be equivalent to MRRC, but it is very much better compared to all the other schemes. Let's say the second order diversity scheme. How are you going to do that? How are you going to do that? We will see that. Now, if you compare it with 1 cross 2, 1 cross 3, if you have 3 receivers and 1 transmitter, even 2 cross 2 system can beat that 1 cross 3 by using simple interpretation, simple geometrically involved mathematics if you use it. And just if you use that space and time division, you can just with that improvement, you will get a better BER. So how do you do that? That we will be studying in the next class. Now remember one thing, from now on, whatever we study, we have to study with a practical scenario, keeping the practical scenario in mind. Not a lot of mathematics will come into picture from now on. So only these things, whatever you have seen, if you read it 2-3 times, you will definitely understand. But core concepts, if you miss, nobody is responsible for that. So you please don't miss core concepts of it. Don't miss it. Don't miss it. So don't miss the next class. Even in 4G systems, in a dense correlated environment, still this Alamoti scheme is used. Till 4G, Alamoti scheme has been used. From 1998 till 2019, 2020, still that Alamoti scheme is used. Not every time, of course, and when it passes through some difficult weather patterns and passes through difficult environments wherein you have lesser signal power available at the transmitter or at the receiver. So Alamoti scheme is a very rugged scheme. So that will give you a performance which is almost equivalent but lesser than MRC. That is for 1 cross 4 MRC. So that is it from my side for today's class. Okay. Don't get frustrated because of the mathematics part of it. You will understand slowly. You will understand because it took a lot of time for everybody to reach to that level of MGF, Chernoff bound, and everything. So just try to remember those equations. Try to solve problems. That would be sufficient for you as an engineer now. When you go for higher studies, definitely you will understand. Definitely, if you are using signal processing or if you're going with some part of linear algebra and mathematics, you will definitely understand all those things. Definitely, most definitely. So in the next class, please don't miss the next class. We will have an analytical approach for no CSIT. Okay. And then we will show you what is a keyhole channel and how exactly the performance of the keyhole channel is deteriorated and how the rank will be won. Any questions? No questions in this class. Please go ahead and just look at those implementation issues and mathematical part of it, and you will understand most of the things. Anything? Okay. Now, generally, whatever I have covered in the previous session and in this session will not be covered for BTECs. Generally, it is not written. Direct formulas are written that make no sense to me. Even if you're stuck somewhere, you have to understand. You have to understand how exactly it has been derived in this fashion. That is why it may be a little hectic to class. I completely understand that. But if you don't understand the significance behind deriving mathematical upper bounds, then there is no use of doing it. There is no use of doing it. Okay. So that's why it looks chaos here and there. Okay. If you have any clarifications, you just message me or mail me, whatever. From next class onwards, we will be starting off with the implemented. Here and there mathematics will come, but not a raw mathematics what we had derived so far. But CDF, PDF, diversity schemes will always be there, not upper bound kind of stuff, upper bound or a closed form solution kind of stuff. So hold your breath, read it carefully. Okay, I'll not gonna ask you any stuff like derive probability of error for MRC or something like that in the exam, but you should know that. You should know that. So generally, most of the IITs follow this pattern. So we will try to, if not at least 50 to 60% of it, we will try to follow. If there are no questions, then we will leave. Anything? Cool. Then we will meet on Thursday. That is 29th. Okay. We will meet on Thursday. Please don't miss the Thursday's class. Anyway, it will be a lockdown if you are in Karnataka. So please try to attend Thursday's class. That's a very important class. Starting from the paper, from his paper, we will try to do it. Okay.
Excuse me, sir.
Simple transmit diversity scheme for wireless communication. How to use space and time, both. Okay. Okay then. All the very best. See you.
Thank you, sir.
Bye-bye.
Excuse me, sir. When will the quiz be?
Yuvraj, yeah, you were saying something.
Sir, at what time will the quiz be on Thursday?
It has not been scheduled. I'll let you know by Wednesday.
Okay, sir. Thank you.
Just message me once over WhatsApp or something like that. Just message me. I'll let you know.
Yes, sir.
Yeah, done. Cool. Bye-bye.